everyone, thank you for joining me today as I present the findings of our latest research paper with the title Rule by Rule, Learning with Confidence Through Vocabulary Expansion that I, Albert Nössig, have prepared together with my two colleagues, Tobias from the RTO Data Lab and Georg Moser from the University of Innsbruck. In this presentation, I want to give you an insight in the basic ideas, as well as the motivation behind the underlying project, and outline the main results and their implications. Thank you in advance for your attention, and let's start with an overview of the topics that we will cover in the following. First of all, I will introduce the basic ideas behind explainable artificial intelligence, together with some advantages as well as limitations of existing methods. In the course of this, I will present a use case from insurance industries that originally inspired us to investigate this field and also motivated the approach introduced in our paper. After that, I will summarize our journey of tackling the aforementioned limitations of explainable methods and outline the main ideas and results of our previous work that ultimately led to the iterative approach, which I want to introduce in today's presentation. And concerning this, I will start with insights in the basic methodology before showing you the results of our empirical evaluation conducted on some standard benchmark datasets, as well as on the use case from insurance business. And finally, I will summarize the key points and give an outlook on some ideas we have in mind to further improve our approach. So let's start off with the fact that artificial intelligence is not only commonly applied in nearly all areas of industry, but has also become an integral part of our daily lives. However, beside all of the advantages we gain by the application of AI, there is at least one issue we should keep in mind regarding its usage. Usually, AI models are highly complex and depend on millions of parameters, making them a so-called black box that lacks explainability and interpretability. To circumvent the problem of opaqueness, explainable artificial intelligence has become more and more popular in recent years, benefiting especially from the transparency of the applied methods. For instance, the construction of easily comprehensible if-then-else rules, like the one shown on this slide here in the context of diabetes prediction, is a popular subfield of XAI, and in particular investigated by us. Here, for instance, we can simply check if the blood pressure and the insulin value of a patient is within the demanded range here, and if this is the case, then we can conclude that the patient suffers from diabetes. Especially in areas where decisions can deeply affect human lives, the application of such transparent methods would be favorable. Beside healthcare, insurance industries is another example of such an area where explainability of the decision-making process is highly desired. And in a collaboration with the Allianz, which is an insurance company offering health insurance services in Germany, we identified in particular the following use case that has served as an inspiration for our work. Every day, an insurance company receives numerous bills handed in by the clients asking for reimbursement. And simply put, the insurance determines the amount of reimbursement depending on the kind of service that has been cleared. On such a bill, there is various information that can be useful to make a correct classification. For example, the amount to be paid, the date, and many more attributes can be used in order to classify a bill, or more precisely, one certain row on such a bill, as material costs or treatment costs, for instance. Unfortunately, I'm not allowed to go into further detail about the available attributes due to a confidentiality agreement, but the basic idea should be clear now. And this use case of decision-making was the start of our collaboration with the Allianz. At first, we solved it by applying quite complex neural networks with several millions of underlying parameters, but as already mentioned, the application of easily comprehensible rules would be preferred in this context, since it's important that the clients as well as the employees can trust the underlying models and understand them at least to some extent, which is not the case considering black box-like neural networks. So let me continue with the second point on today's agenda and summarize the main limitations of classical rule learning methods and our approaches to overcome these defects. So in first experiments, we tried to apply in particular various methods from the fields of inductive logic programming and rule induction in this context. But before concretely introducing the limitations we observed when applying these methods, as well as our proposed solutions, let me start with outlining the principal idea behind rule learning algorithms in general. So basically, the input consists of labeled data, as for instance, specific blood values from patients together with their health status, as considered in the example shown on the previous slide. Depending on the label, the input data is split into positive and negative examples. Assuming that we aim to identify the patient suffering from diabetes, the corresponding instances are used as positive examples, whereas the healthy patients serve as negative examples. Now a rule can be generated step by step, one condition after another. Here the exact way of proceeding varies for the different algorithms, but in principle all possible conditions are considered, and depending on a certain gain function, the best one is chosen. And the choice of this gain function used in a rule learning algorithm is a key characteristic that defines the methods, since it determines how the algorithm evaluates and selects the most informative rule during the learning process. However, at the end of the day, a rule should always cover as many positive examples as possible and as few negative examples as possible. So in this illustration, for instance, I illustrated the positive examples as these green pluses and the negative examples as these red dashes. And the first learned condition could consider, for instance, the blood pressure. And for the induction of the next condition, we restrict to the examples within this demanded range here. Then the next condition with highest gain is added to the rule again. And this way of proceeding is repeated until no negative examples remain in the considered area or a given total number of conditions is reached. Then the completed rule is stored and the covered positive examples are removed from the considered data. And afterwards, the next rule can be learned analogously. This is repeated until all positive examples are covered by at least one rule or a given total number of rules is generated. And at the end of the day, we obtain a rule set that can be used for binary classification by differentiating between the given positive and negative examples. So at this point, we are aware of the basic idea behind rule induction in general. But to ease the understanding of the following, we should have a look at the way multi-class classification using these if-then-else rules is done by us. So in the first step, we learn rules and construct binary classifiers for each possible label, as outlined before. For instance, considering the MNIST digits dataset consisting of images of handwritten digits, we obtain 10 independent sets of rules, where each rule set can be used to predict whether the given image depicts the corresponding digit or not. So let's assume, for instance, that this image here is given, and our goal is to predict the depicted digit, which is obviously a 0. And for this purpose, we successively apply the 10 binary classifiers learned in the first step and combine the obtained predictions to a binary vector, where 1 corresponds to true and 0 to false. This yields a 1 hot encoding of our multi-class prediction, and finally we can return the predicted class, so in this case the digit 0. Of course, it's not always that simple to obtain a multi-class classification. It might occur, for instance, that 2 or more binary classifiers return true, resulting in an ambiguous multi-class classification. In this case, we additionally take the length of the learned rules into account and return the label corresponding to the satisfied rule with the most conditions. On the other hand, if no binary classifier returns true, we consider the percentage of satisfied conditions and predict the label with highest percentage. This way of proceeding is often referred to as partial matching and is common practice in rule learning. Now, as we have a basic understanding of the way rules are generated and used for multi-class classification, we can discuss the observed limitations of the classical methods together with our approaches to resolve them. First of all, the classical methods are mostly designed to work with only very few examples, and it quickly became clear that the application of such methods is not straightforward when very large datasets with several thousands of input examples are considered. And our use case of interest from the insurance business considers a dataset with nearly 1 million examples. So as a first step towards the application of explainable methods in the company, we investigated this problem in detail and introduced a modular approach, making it possible to apply common rule learning methods such as FOIL and RIPPER, for instance, in reasonable time on very large datasets. Basically, the approach consists of 3 independent phases, as depicted on this slide here, but the crucial one is the phase here in the middle, the input selection. The preceding step of representation learning is mainly done to ease and improve the input selection by dimensionality reduction, and the subsequent step basically comprises the application of the chosen rule learning method. On this figure, I included examples for methods that can be applied during each phase, but in this presentation, I want to set the focus on the crucial phase and outline the advantages of a meaningful input selection. So basically, we split the whole problem into several subtasks. As a representative example, I will use the MNIST digits dataset again. Remember that the goal is to predict the digit depicted on a given image. So considering the digit 0 in particular, we can clearly differentiate between different forms of writing it. There are straight zeros, round zeros, and slanted zeros, for instance. And remember that a rule learning algorithm basically aims to find rules describing a given set of positive examples. So instead of using all of these various forms of zeros as one large set of positive examples, we split the set into 3 subsets consisting of very similar positive examples by applying clustering. This eases the process of rule learning since the learner can focus on one certain form instead of additionally differentiating between round and slanted zeros, for instance. So at the end of the day, we consider 3 independent subproblems and apply the rule learning method on each of them. In this illustration here, we can also see some example rules underneath each cluster. The red markers correspond to an expected black pixel, while the blue markers demand a white pixel, and each marker style represents a separate rule. And obviously, the rules learned on each cluster exactly match with the form of the underlying zeros used as positive examples. Afterwards, the rules learned on each cluster are concatenated and can then be used to predict whether a given image shows a zero or not. Moreover, another advantage of this form of input selection is that we can compute the rules on each cluster in parallel, which saves a lot of computation time, as shown with the example of our use case from the insurance business. Here, especially the FOIL algorithm benefits from our approach, showing a speed-up factor of nearly 45, meaning that instead of a computation time of about 3 days, it is finished after less than 2 hours, yielding approximately the same classification accuracy. And also for the Ripper algorithm, we could accelerate the computation by a factor of nearly 4. However, we directly faced another issue, that is a common limitation of XAI tools and rule learning in particular. The performance of the explainable methods with respect to classification accuracy has been significantly worse than the one achieved with the previously applied neural networks. So we had to balance between full transparency and the quality of the outcomes. And in order to tackle this so-called interpretability accuracy trade-off, we introduced a voting approach combining explainable and unexplainable methods. The basic idea is illustrated on this slide here. Based on the modular approach from our first paper, we generate rules with FOIL and Ripper, for instance, and use them for classification. In the first step, we only compare the predictions from these 2 explainable methods, and in case they coincide, we return this prediction as final classification, justified by one rule from each method. Otherwise, if the predictions from FOIL and Ripper differ, we additionally incorporate an unexplainable state-of-the-art method, which we call decider in the following. And simply put, the decider tells us which rule learner is right, and we use the according prediction as final classification, again justified by the corresponding rule. So we can use, for instance, a neural network as decider here, and if the network predicts a 0 for this input example, this means for us that we should use the satisfied Ripper rule and predict a 0 based on this explanation. The more complicated cases, where the decider does not coincide with any of the applied rule learners, are handled by some additional checks concerning the number of satisfied conditions of each rule. But I will not go into further detail about this right now. So at the end of the day, this approach yields so-called end-to-end explainable classifications, meaning that the final classification is justified by an easily comprehensible rule, while the steps in between can be supported by the advice of an unexplainable method. Although the full transparency of the original method is now replaced by end-to-end explainability, the trust and the basic understanding of the underlying model is still assured. Moreover, the evaluation shows that this way of proceeding can significantly improve the performance of explainable methods and makes them a competitive option for decision-making in a production environment. For instance, we considered the MNIST digits as well as the dental bills highlighted in this table here, besides some additional benchmarks. And this table shows the accuracy of FOIL and Ripper on each dataset, as well as from a neural network that has been used as decider. However, note that we did not spend too much time on tuning the decider here. But basically, we can observe that the result from our voting approach is always almost as good as the chosen decider. And on the fashion MNIST dataset, which is very similar to the MNIST digits, but contains images of pieces of clothing, the accuracy from our method is even 3% higher than the one from the neural network used as decider. So at this point, we have introduced a framework making it possible to apply common rule learning methods on very large data sets in reasonable time, while achieving results comparable to unexplainable methods. However, in particular concerning our use case of interest from insurance business, there is still one missing piece. Remember that the underlying data consists of bills that contain a lot of text. but the textual information has never been considered up to now. We have always used the pre-processed data consisting of nominal and continuous features that has been provided by the company. Nevertheless, there would be a lot of additional information in the text, which we also want to include in our framework for explainable classifications. And as a consequence, our current work focuses especially on the handling of text-based data in the context of rule induction. And in the following, I want to explain in more detail the principal problem as well as our approach to solve it. So in this work, we forget for a moment what has already been done in our previous work and consider the classical rule learning methods with the aim to improve their performance in the context of text-based classification. At the end of the day, we can combine the iterative approach introduced in this paper with the already existing framework from our previous work and obtain an approach that is perfectly suited for problems considering a combination of nominal and textual input data. But first, let's discuss the main problem concerning the application of rule learning methods on textual data, namely the choice of the underlying dictionary or vocabulary. Usually, the textual input is transformed into binary vectors considering the occurrence of certain words or phrases in the text. So 1 if the word appears and 0 if not. For example, the vocabulary defined here results in the following transformation of this sentence. The words example and sentence occur, so the corresponding values are equal to 1, whereas the remaining entries of the vector are equal to 0 because the words rule and question do not appear in the example. And at the end of the day, we have to deal with the question of how many and which words we should consider in the underlying vocabulary. A small vocabulary often leads poor results because the considered words do not suffice to distinguish between similar classes. And on the other hand, a very large vocabulary goes hand in hand with extensive memory and time consumption, which is not feasible even with our modular approach. And as a trade-off, we propose an iterative approach starting with a small vocabulary, especially suited for distinguishing between very heterogeneous examples. To learn rules differentiating between similar examples corresponding to different classes, we iteratively increase the size of the applied vocabulary as illustrated on the following slide. So as explained before, the textual input data is transformed into binary vectors, making use of a previously defined vocabulary of size n, where n is rather small at the beginning. So typically we use 1/8 of the total number of attributes. And note that the transformed data here is split into a training, a test, and a validation set. Then we apply the chosen rule learning method, such as FOIL or Ripper, for instance, on the training set, and obtain one rule that considers the occurrence of the n words defined in the vocabulary. The generated rule is subsequently evaluated on the validation set and equipped with a so-called value of confidence introduced in our paper. There is no unique definition or formula for this value since it's more useful to define it depending on the underlying use case, but basically it states how accurate the rule is. So considering the dental bills from the insurance business, for instance, it is crucial that the predictions are correct. And it is better to not give a prediction at all than a wrong prediction, since each example that can be processed without the intervention of a human is already a benefit. And in such a scenario, the precision is an appropriate choice for the value of confidence, and we applied this metric in all of our experiments. So here P denotes the number of covered positive examples and N the number of covered negative examples. A more detailed investigation of different metrics in this context will be done in future work. However, at the end of the day, this value is used in order to decide whether the generated rule has a satisfying quality. For this purpose, we define a threshold that basically again depends on the underlying use case. So typically we use 0.9 as threshold in our experiments, but we will investigate the influence of this value on the results in a moment. Eventually, the rule is stored if the value of confidence is higher than the chosen threshold, and otherwise the vocabulary size n is increased, and a new rule is generated considering a larger number of words. This way of proceeding is repeated for a previously defined number of iterations. And if the rule resulting from the final iteration still does not satisfy the quality specified by the threshold, we remove the currently covered examples, like in classical rule learning, but do not include the rule in our final rule set. Because sometimes it can happen that we are stuck in a kind of local optimum, and after removing these examples, the algorithm most of the time returns rules of satisfying quality again. Otherwise, we also include early stopping in case no rule of satisfying quality is generated for a specified number of consecutive iterations. And now with a basic understanding of the key concepts of our proposed iterative approach, we can use the remaining time to discuss the results from our experimental evaluation. So first of all, we considered some standard benchmark datasets for text classification, namely the hate speech dataset, Reuters, and IMDb. We always applied the methods FOIL and RIPPER and compared the outcomes and resource consumption of the classical method with our proposed iterative approach. The first dataset here is a binary classification problem, considering the appearance of hate speech in Twitter posts. Concerning memory consumption, we could approximately halve the necessary resources for both algorithms, and also the classification accuracy is increased significantly. For instance, for FOIL, we achieve a 4.5% higher accuracy than the classical approach. Similar results are obtained for the Reuters dataset, which is a multi-class classification problem, assigning news documents to the according categories. Especially the FOIL algorithm benefits from our iterative approach, with an accuracy increased by nearly 10% while reducing the memory consumption by about a third. And finally, we considered the IMDb dataset, which consists of movie reviews in informal language. In this case, the underlying vocabulary is extremely large, such that we had to restrict the total feature space for our experiments with RIPPER. As a result, the memory consumption here is lower than the one observed for FOIL, which is usually the other way around. However, again, the memory consumption could be reduced significantly for both methods, and for RIPPER in particular, we can observe a clearly higher accuracy. For FOIL, the results are approximately equivalent, but we believe that a more sophisticated pre-processing of the input data would be especially beneficial concerning this dataset, because the movie reviews contain quite some typographical errors and slang words which might affect the construction of the underlying vocabulary. So we will investigate this in more detail in future work. However, as already mentioned, our approach is not limited to textual input data, but also shows advantages for nominal and continuous datasets. Concerning this, we considered some standard benchmark datasets that have already been extensively studied in our previous work. Here, we do not change the feature space, but only investigate the influence of our proposed value of confidence on the quality of the generated rules. And indeed, we observe a clear increase of classification accuracy on most of the considered datasets. And finally, for our use case from the insurance business, we investigate the influence of the value of confidence in more detail. Here in each row, we ignore all rules with a value of confidence lower than the stated threshold. Then we consider the total number of examples where a prediction is made based on these rules. So in other words, this column titled predicted shows the number of examples where at least one rule is satisfied. Then the next column gives the number of correctly predicted examples, and the last one shows the corresponding precision or accuracy in percent. And at the end of the day, this table shows exactly what we aimed for. The precision clearly increases with an increased value of confidence, making it possible to classify about 120,000 examples with FOIL, for instance, with a nearly perfect precision. And this is about half of the considered test examples that can be processed without human intervention by applying fully transparent and explainable methods. So before coming to an end in a moment, I want to quickly summarize the key points of this presentation and outline some ideas for future work. So all in all, our proposed approach focuses on progressively expanding the vocabulary used in each iteration, resulting in a significant reduction in memory consumption. By additionally leveraging the value of confidence introduced in this paper, our approach ensures that only the most robust and trustworthy rules are retained, thereby enhancing the overall quality of the rule learning process, resulting in a significantly increased classification accuracy. Moreover, the ideas introduced in this paper are not only beneficial for textual input data, but also for nominal and continuous data. Eventually, the combination of the proposed approach with our previous work provides a framework enabling the application of common rule learning methods in a large variety of use cases, and it already has an impact on the way automated decision-making is done in insurance industries. Regarding future work, we aim to improve the choice of the vocabulary by more sophisticated pre-processing, using large language models, for instance, and moreover, using computer vision approaches in order to incorporate the position of words in a document might be another interesting consideration we aim to investigate in future work, because especially in our main use case concerning reimbursement, The considered bills are mostly standardized, and the crucial information is typically located in a specific area of the document. And now I want to thank you all for your attention and look forward to any questions or feedback you may have. Thank you.